Thank you very much. Let me introduce myself a little. So I'm a neuroscientist at Tokyo University. I initially started as a theoretical neuroscience, but at some point I got really hooked on into consciousness science. And in the end, I moved to Max Planck, Germany, and then was the world capital of experimental consciousness research. And after publishing a science paper, an ordinary consciousness project, I got over with my craving for top journals, and I thought maybe I need a Nobel Prize. I'm just kidding, so you should laugh, okay? But this digital immortality part actually stems from my approach to decipher neuromechanism of consciousness. So let me ask the audience, who don't want to die? Okay, so who's okay dying? Yeah, so I usually get like 10%. So here I'm here to rescue the rest of the 10%, okay? So what is the biggest fruit in invasive brain-machine interface? So looking at this, the social cost of brain disorder, it is obvious that we should replace damaged brain areas with artificial neural networks. An alternative method would be to, for example, implement culture cells in your brain and keep your fingers crossed that the neurons hook up. But for example, it's very hard to imagine that we can recover lost language functions. But on the other hand, if we already have a built-in AI with language capabilities, and if we are able to hook up this AI, just as the two regions of brains are hooked up at the neural level, it would be a beautiful solution to the problem. So we do need, to pull this off, we do need read-write performance at the neuronal level. So let's look at the chart. These are all big American startups for brain-machine interface, all invested like hundreds of millions of dollars. You can see that they're all flatlined in terms of precision, writing precision. And let me tell you why. Okay, that's where mine goes, okay? So the problem is that all these conventional BMIs work in the gray matter. And if you want to write in precise information, that means you need to stimulate this single neuron per channel. But the problem is, in the gray matter, the nerve fibers are all tangled up, and no matter how much you lower the current, given that you can still stimulate this, it keeps on stimulating all the axons in between, and it would activate distant neurons, which you cannot actually read. So this is hence the shooting a shotgun in the dark effect, and in the gray matter, we cannot achieve this AI replacement. So here comes my proposal. Might be a little surprise. So what I do is instead of using the gray matter, I use the corpusculum or nerve bundle fibers. I dissect them and attach a CMOS-based high-density multi-electrode array. The good thing about nerve bundle fibers is that, well, first of all, neuron soma does not exist, so you're going to read the axons in the first place, the nerve fibers, and these axons are all aligned nice and straight. So it is easy to accomplish one-to-one correspondence between what you read and what you write. And if you're worried about the surgical procedure, we still have this corpusculostomy, the modern version of it, and it's going to be very similar to that. And one other advantage of this BAD-BMI is to use it in the corpusculum is that you have a full coverage of the neocortex, which is very difficult to achieve with other methods. So why now? So one thing is that now we have commercial-grade CMOS electrode arrays that actually work. Second, demonstration of presynaptic formation on the metal surface using this neurology neurolexin biomolecule. So you can, if you're any expert in neuroscience, you might think, well, if you cut the axon, what are you going to do about it? You need to rescue them, but there's very good hope that we can actually rescue them by coating this biomolecule. And the good thing is, we're not starting from scratch. I have a academic lab at Tokyo University. In vitro work, we do experimental platform for synapse formation. And for vivo work, we inserted the CMOS array called the neuropixels into the mouse corpusclosum, but not dissecting it, but along the fiber. And we managed to actually read the so-called action potentials or the output of neurons. And now we are working on the pinpoint writing procedure. But the problem is, it is a quite good big lab. It's going to be like size of 20 next year. But unfortunately, in academia, it takes forever to get things done. And if I keep up this pace, I'm doomed to die. And you too. So here's the program sector to fill the critical gap in 3 years. First, in vitro and vivo deployment of electroaxonal connectivity, the synaptic formation, and demonstration of read-write capability. And finally, in vivo development of close-loop AI user interaction. So what do we get? Axonal synaptic channel that enter at a surface, neuronal level read-write access, and verification of AI replacement of brain circuitry. So we have a safe net plan. If all fails, or at least the vitro part works, we can have a in vitro testing platform, drug discovery. We have problems in the central nervous system. You can go for peripheral BMI. And this is the present for most of you, the 90% of you, the AI replacement of damaged brain circuitry. And finally, I'll talk about my scientific dream and my desire for digital immortality. Oh shit. Okay. So you can read my book, okay? Thank you very much.